Okay, in 1.1, we're going to start talking about rate of change. In a calculus, a lot of it will be rate of change, and can you measure the rate of change at an instant? Okay, so we're going to go ahead and look at this first function over here. It says Joe's distance from his house is modeled by the function d of t. While riding his bike to the store, he realizes he dropped his wallet and turns around to find it. After finding his wallet, he finishes his ride to the store. Okay, the first question is, what is his average speed or his rate of change for his trip to the store if he arrives after 8 minutes? So I'm finding the rate of change from when he starts until 8 minutes. So he starts right here. At 8 minutes, he's up here. So if I draw the line of that segment, I want to find the rate of change there. Rate of change, you've heard it before. Rate of change is the slope. And in this case, this line that goes from this point to this point is going to be called a secant line. Okay, if you remember slope, slope is change in y over change in x. Since this is the graph of d and it's over the time minutes, we're going to call it change of d over change in t, or the change in distance over the change in time. So from 8 minutes to where he started from, that's the change in his distance. Change in time, 8 minus 0. So at time equals 8, he's at 1300. D of 0, well, he started at 0, 0. So 1300 divided by 8 is going to give me about 162.5. Okay, this is rate of change, so the units are important and they help us analyze what we're talking about. So in this case, the numerator was the distance. The distance is given in meters. The denominator is the change in time. Time was given in minutes. So this is meters per minute. Okay, that could also be written as meters per minute. Okay, now let's say we want his average rate of change between 2 and 6 minutes. I'm going to use the graph again, but this time I'm going from t equals 2 minutes to t equals 6 minutes. So t equals 2 is up here. T equals 6 is down here. If I draw the secant line, okay, I'm going to try to find the slope of that line, which is also the d of 6 minus d of 2, or the distance at 6 minutes minus the distance in 2 minutes over 6 minus 2. Okay, I'm not actually going to calculate it, but that's how I would set it up. If you look at this, the slope of that line is negative, so I would actually have a negative rate of change. And say I wanted to find his rate of change from 2 to 3 minutes. Let's look at the graph. That would be d of 3 minus d of 2 over 3 minus 2. And if I look at the graph, let's see, d of 3 is around here. D of 2 is right here. So I'd be finding the slope of that line, which is actually pretty flat. So it's probably a little bit positive, but pretty close to 0. Okay, now the question is it possible to know how fast he is going at an instant? Okay, if you look at the graph up here, each of these secant lines had very different slopes. So he's going different speeds at all kinds of different points. So they want to know, could you figure out what he was going at an instant? You can, and they call it the instantaneous rate of change. Let's write that down. Okay, but the question is, how do you even do that? Okay, so we can't get an exact value, at least not yet, but let's try to get close as we can to it. So say I wanted to calculate a rate of change that would give as close to an estimate as I could to the instantaneous rate of change of 2. Okay, so I still need to use the same formula, the change in d over change of time, but I want to pick a time that is very, very close to 2. So maybe I do d of 2 minus d of 1.99999. Is that an instantaneous rate? No, but I'm trying to make the 2 points as close together as possible. So it's happening over such a short time span that it becomes really, really close together. I could have also chosen maybe d of 2 minus d of 2.001 or some other point that is very, very close. I want to pick the 2 closest points as possible together. Okay, for E, I'm just going to give a rough estimate of the instantaneous rate of change at t equals 2. Okay, so I'm going to go back up to the graph, and I'm going to use the graph to make this estimate. Okay, now at t equals 2, where is t equals 2? T equals 2 is this point right here. I'm going to draw the tangent segment to that point. Okay, a tangent segment just touches the graph in one spot, so this is a tangent line, whereas the secant lines that we drew over here intersect the graph at 2 points. So this is tangent, it's just touching the point at t equals 2. I would just estimate about what the slope is right there. Let's see, if I went up from here to here, maybe 120. If I went from here to here, maybe about 1. So my guess of what maybe the slope would be there might be 120 minutes over 1 second. Is this a guess? This is totally a guess. So maybe it's 120 meters per second. Given that my graph was horrifically inaccurate, and so estimating is not the best way to find it, we will find better ways to do it in the future. Okay, now we're just going to practice interpreting the information given by a function and its rate of change. Okay, so B of t represents the buffalo population in the United States, where t is measured in years since 1800. So the first question is, what does B of 90 represent? So that's saying at t is 90, 90 is the time in years past 1800, so that's in 1890. B represents the buffalo population, which means that B of 90 represents the buffalo population. Um, 90 years since 1800, so in 1890. Okay, now the next thing is saying, what is B of 50 minus B of 0 over 50 minus 0? I know that's a rate of change because it looks like the slope formula. So this is going to be the average rate of change. Change of what? Let's see. The numerator is the buffalo population in the United States. This is the time from, let's see, 50 years past 1800, so 1850 to 1800. And when you're interpreting it, make sure you're considering the units. This was the buffalo population. This was in certain years. Those have to be included every time you write this. Okay, now let's look at the last one. What should be C? Let's make it a C. Okay, so what does this represent? This is still a rate of change. It's going from B of 32 to B of 31.9999. So it seems like it's an estimate or an approximation of the rate of change, the instantaneous rate of change of the buffalo population in the U.S. in, 32 years since 1800, in 1832. And then just glance back at it and make sure you included something about the units. It was the buffalo population in terms of a year.